Next, 24. Exercise 24. So we have to describe here all the homomorphisms alpha from Z10 into Z15. And the solution goes like this. So let us first see, if we assume such a homomorphism, then what is the consequence? What is it that we get from such a function? Let alpha be a homomorphism. Then we can use one result from this section immediately by theorem 4.3, and in fact, well, it's not 4.3, sorry, it's 4.10. Part 3 of that theorem, it has 3 parts. By part 3, we have this conclusion, that the order of the element alpha of 1 divides the order of 1. Well, this order you understand, since alpha of 1 is an element in Z15, it's the order of alpha of 1 in this group. But this 1 is coming from Z10 or Z10, so its order in Z10 is its order in Z10, which is 10. But something else also we know. Since alpha of 1 after all is an element of this group, so its order has to also divide the order of this group. And the order of the second group is 15. So that means the order of alpha of 1 has to divide both 15 and 10, from which we of course get this conclusion. Hence, this order divides 5, because it divides 15 and 10, so it should also divide 15 minus 10, which is 5. But 5 is a prime, and the order of an element by definition is a positive integer. So there are only 2 possibilities. One of them is of course this, and the other one is 5. Now let us see each one of them separately. If the order of alpha of 1 is 1, then alpha of 1 will be the identity element in this group, of course, because alpha of 1 belongs to this group. That is because in any group the only element whose order is 1 is the identity element. But the identity in this group is 0. So in this case, we can say in fact what the actual homomorphism alpha is. I mean, at once we can say. For any element x in the domain group, we have alpha of x equal to x times alpha of 1. You do understand how we are getting this. That's because in our group Z10, x is 1 plus 1 plus 1 and so on x number of times. That is, here we are actually looking at a sum where all the terms, all the summands are 1 and there are x of them. So because alpha is a homomorphism, that would be equal to the sum of that many alpha of 1s. So that's why x times alpha of 1. But now alpha of 1 is nothing but 0. So if you add x times 0, the 0 means the 0 element here. So you just simply get 0. So in this case, we get that homomorphism which maps all the elements of Z10 onto the 0 element of the second group. So this happens when this condition is true. On the other hand, if the order of alpha of 1 in the second group is 5, then of course you will have to look for those elements in Z15 which are of order 5, and they are these. Then alpha of 1 belongs to, this is just simply a matter of going through all the elements and their orders. You will find that those elements are these. And for each such choice of alpha of 1, we are going to get one homomorphism. For each of these 4 choices, we get a homomorphism alpha given by alpha of x equal to x times alpha of 1, where x of course is coming from Z10. So that is the solution. Next, the 25th one, let G be a finite group and alpha from G into H and onto homomorphism. Then there are 2 parts it's about finding some elements of given order. If G has an element of order n, if G has an element of order n, must H have 1. and number 2 visits opposite. If H has an element of order n, must G have 1. So what is given to us? It's given to us that this is a homomorphism fine, but an onto homomorphism, a surjective homomorphism. Then we have to answer these things. The first one is not necessary. So in the first one we are asked that if G has an element of order n, where n can be anything, is it necessary that H also should have an element of order n? And that's not necessary because of this. Not necessarily. For example, if G is a group of order greater than 1, if G is a group of order greater than 1, but H is the trivial group consisting of only one element, that means H has order 1, and alpha of x is equal to E for all x belonging to G, then okay, I think I haven't been able to put it nicely. No, this is not quite right, but the way I have written it here, well, I can just simply provide one concrete example, or something at least that has n in it. Consider, well, not necessarily, of course, I should not have erased it. Not necessarily. Consider the cyclic subgroup, or cyclic group, I mean. Consider the cyclic group G equal to this of order, that means its generator is A. A is one of its generators. Order n, and H is the trivial group, and alpha of x, actually this x, since this is a cyclic group, this x will be a power of A, but we can just simply write x is equal to E for all x belonging to G. Then order of A obviously is in G, is n, but there is no element in H of order n. And in this example, obviously we are assuming n to be greater than 1. That's why we write not necessarily. We are not writing that it will never happen, but not necessarily. If you take G also to be the trivial group, then of course it's true, because the only n in that case is 1, and there is of course only one element in H which has order 1. In that case it's true, but in general it's not true. But the second one is true. If H has an element of order n, must G have 1? Yes. But how? Let's see. Let H belonging to H be of order n. Now we are given that our homomorphism is onto. Since alpha is onto, so this H is equal to the alpha image of some element G in G. For some G in G. Now we are again going to use that result that we have used just now, that is theorem 410 part 3. Why? Theorem 410 3. What does that theorem say? It says that the order of alpha of G divides the order of G. But there is a condition. G should have finite order, of course, because otherwise it would not make any sense. Let's just write the conclusion and then we will mention that G has finite order because of something. But what is the order of alpha of G? That is n, because alpha of G is nothing but H and we have assumed it to have order n. This should divide the order of G. Note that the order of G is finite since capital G is a capital G is a finite group. Is it? Yes, it is mentioned. Yeah, in the problem it's mentioned. This is a finite group, so all of its elements must have finite order. So in particular this small g also has finite order. So that means what? That the order of G will be a multiple of n. Let order of G be equal to nm for some integer m. I need ink, excuse me. And from this condition now we will be able to find an element of order n in G, in capital G. And that element is nothing but the mth power of G. From the formula that lets us calculate orders of powers of some elements in terms of orders of order of that element, from that thing we then get this. But then this is an element in G such that its order is n. So that's how we get an element in G whose order is also n. So the second part is necessary. I mean, it is true. It will be true. So that is the solution. Next, let alpha from, again I think, G into H be a homomorphism. So here also it's given that alpha is a homomorphism, and suppose that alpha of G is equal to H. Okay, for any element A in G, show that alpha of A is also equal to H. Just like alpha of G is H, alpha of A is also equal to H if and only if A is equal to GK for some K belonging to the kernel of alpha. This one is very straightforward, so let's see the solution. Let's do that there. So that means we have to prove two implications, namely that this condition is necessary as well as sufficient for these things to happen. So which one shall we do? Let's first assume that we have this and then show that the alpha image of A is also H. That is, I think, the easier one. Let A be equal to GK, where K is some element in the kernel of alpha. Now it's just a matter of calculating alpha of A using the fact that alpha is a homomorphism. Then alpha of A is equal to alpha of GK, but because alpha is a homomorphism, this becomes alpha of G times alpha of K. Now, since K belongs to the kernel of alpha, alpha of K will be equal to the identity element in H, which we are just simply going to denote by E. Okay, but that is nothing but alpha G, and this is H. So that's how we get the fact that alpha of A is also equal to H. Conversely, let alpha of G be equal to alpha of A. That is, actually this is already something we have. This is a part of our hypothesis. But what now we are assuming is this, that alpha is an element in G. A is an element in G whose alpha image is also equal to H. Then, now note that A can be written like this: G times G inverse A. That is just simply, one can see that G and G inverse will cancel out, leaving us with A. where, but now our aim is to show that this G inverse A belongs to the kernel of alpha, because then we have the required form that A needs to be in. So we calculate the alpha image of G inverse A. Because alpha is a homomorphism, first it distributes itself over this product. But again, because it's a homomorphism, alpha of G inverse is the inverse of alpha of G. It's a property of homomorphisms. Now, since alpha of G is equal to alpha of A, this product is nothing but the identity. And identity where? Identity in H. This shows that G inverse A belongs to the kernel of alpha. That means we have expressed A as an element, well, not any element, but this particular element G times something, and that something actually belongs to the kernel of alpha. So that's what we wanted to show. So this is the solution. And finally, let's solve one more. This one is very nice. It looks quite nice. Define alpha from G times G into G. So here alpha is a function, and the rule for the function is just this. So you can see that this alpha is actually nothing but the binary operation in G. That's what it is. It's nothing else. The binary operation written properly. That is, if you interpret it as it is after all a function, but if you write it properly, rigorously like this, then it will look like this. Now, if alpha is a homomorphism, that restriction can be imposed on alpha, because this Cartesian product itself is also a group, and G of course is a group. So we may assume that this alpha is a homomorphism. Then the consequence is this: show that G is abelian. Solution. So that means we have to show that any two elements commute with each other. So let G and H be any two elements in G. Then GH from this formula is nothing but alpha of G comma H. But this ordered pair itself can be written like this: E comma H times G comma E. You can see why. If you apply the definition of the binary operation in G times G, which is a component wise multiplication, then the first component of this product will be EG, that is G, and the second one will be HE, that is H. But now you use the condition that alpha is a homomorphism. So this becomes alpha of E comma H times alpha of G comma E. And now you just use the definition of alpha. So alpha of E comma H will be EH and alpha of G comma E will be GE. That is, we get HG. So we have proved that GH is equal to HG. Thus, G is abelian. And that completes the solution, and that completes this video also. We are of course going to solve the other exercises in this section. I think 3 of them are left, so we will do that in the next Lee update. And tomorrow, as usual, we are going to go to analysis, and where we have started solving the exercises. So we will see what exercise comes after the first one that we have already solved. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.